Hi, my name is Carly and we are going to be doing the Interactive Advanced Concept Presentation 3. Today we are going to be doing an acid-base reaction with baking soda and vinegar. So first I'm just going to show you my supplies and we are going to be adding our baking soda. We have a paper towel that we'll put our baking soda in, and we also have vinegar. And I'm also going to be going over limiting reactant and our Bronsted acid and our Bronsted base, as well as our conjugate acid and our conjugate base. So we will go over the math and the equation part later. But first I am going to do 2 grams of baking soda, and I'm also going to be doing 50 grams of vinegar. So I have a scale here, and this is just so we don't make a mess everywhere, but I have my scale. And I'm going to put 2 grams of our baking soda. Okay, so we have our 2 grams. I'm actually going to pour our 2 grams into our paper towel here. And then I will wrap this up. I'm going to make this a little bit smaller. And we're going to put this in here. Okay. Next, I will grab our vinegar, which I'm going to grab another beaker here, and we'll zero this, and I'm going to do 50 grams of our vinegar. Okay, so we have 50 grams of vinegar. And we are going to go ahead and pour our vinegar into our baking soda, and we'll see what happens. So you can hear it starting to fizz. But I think that the paper towel is what is keeping it contained. So let's add a little bit more. I can see that the paper towel is expanding, so that also tells me that a gas is being formed aside from just the fizzing. Like this was popping up a little bit. Okay, so I think the reason why I didn't get a bigger reaction was because it is more contained in the paper towel. So I think this would be like a control. But you can see the bubbles down here actually having a hard time being able to rise. Interesting. Yeah, so I think that the paper towel is was keeping the baking soda a little bit contained, and that's why I didn't see a bigger reaction, but it still occurred. It was still fizzing. We know that there was gas. The paper towel is actually trying to expand a little bit. So let's talk about our equation, and then we will talk about our math. So we have our NaHCO3, which is our baking soda, and this is our weak base. And we have our HC2H3O2, which is our vinegar, which is our weak acid. Both of them are aqueous. And so for our baking soda, that is our weak base, this is our Bronsted base, because it is going to receive the hydrogen that then in turn our vinegar, which is our weak acid, is our Bronsted acid. So it's going to give up the hydrogen. So with our diagram here, we can see the hydrogen goes to the HCO3. So that's what makes our weak base, our Bronsted base. It's going to take this hydrogen, we're going to see it over here. So that forms our H2CO3. And then we also have our sodium combines with our C2H3O2 to form our sodium acetate. So this was also dissolved in the water, and that was the byproduct of our sodium in our C2H3O2. So this is our conjugate acid. It did not receive a hydrogen in our equation, and that makes our H2CO3 our conjugate base, because it is what received another hydrogen from our equation over here. So this is a double displacement. The H2CO3 is not able to readily stay together, so it actually breaks down even further, which makes this the double displacement. It breaks down further to H2O and our CO2, and our CO2 is our gas that we saw whenever we saw the bubbling in the paper towel trying to expand a little bit. That was the gas part of this. The H2O is the liquid, and then what was dissolved was our sodium acetate. So, and everything was neutralized, so this is also neutralization, but it's double displacement from our H2CO3, further breaking down into water and to carbon dioxide gas. So that's a little bit about the equation part. About the math in the limiting reactant. So this is why I use the 2 grams of the baking soda, and I use 50 grams of the vinegar. So on here, you can see we start off with 2 grams of NaHCO3, and I have to convert this to moles. So we do moles equals, 1 mole is equal to 84.007 grams. That's our molar mass for our baking soda. We times that across our equation with 2 grams of the baking soda over 1. So we get 0.02 moles. That's how many moles that we have. So when we put this into our equation, when we put this into our math problem here, we go back to our equation and see that this is 1 to 1. So we don't have any coefficients here. So it's 1 mole to 1 mole. So when we go back, we can see that 0.02 moles of our NaHCO3, when we cross cancel this, we have 1 mole to 1 mole of our HC2H3O2. So that's saying that we need 0.02 moles of HC2H3O2 is required to be able to use this amount of baking soda. So we do the same thing with the vinegar. We had 50 grams of vinegar, or HC2H3O2. We are going to also convert that to moles. So 1 mole is equal to 60.052 grams. That is our molar mass for vinegar. And we times that by, or 1 mole over 60.052 grams times 50 grams is what we have. We end up with 0.8 moles. So we'll plug that back into our equation for limiting reactant, and we'll do 0.8 moles vinegar times, this is 1 to 1 again, same thing from here, it's 1 to 1. So we have 1 mole of HC2H3O2 per 1 mole of NaHCO3, and that tells us that NaHCO3, that it is required that 0.8 moles of this is needed. Now we only had 0.02 moles So that tells us that our baking soda, or our NaHCO3, is our limiting reactant. So that was our interactive advanced concept presentation 3 for acid base. We talked about limiting reactant. We talked about our Bronsted base and our Bronsted acid, and our conjugate base and conjugate acid. And I'm still thinking that this was a successful experiment. I think that the paper towel, maybe if I would have done something a little bit smaller to where the vinegar could have more readily mixed with the baking soda, that we would have seen a little bit more of a reaction. But it still occurred. It was just more contained. I guess you could consider the paper towel as a control. But all in all, I think it was successful. And thank you for watching.